The Constitution of India, Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Happy morning, students. I hope you all are good and almost 4 chapters are over. And see, this chapter states of matter. Till now you have been learning about periodic table, its periodicity, properties, the bond involved in the formation of molecules, and how does the boiling points or ionization atomic sizes vary. Now in this chapter we are going to deal with the states of matter. That is, how does the properties influence a particular state of matter. We will be learning about different state laws, how it exhibits in a gaseous state, and we will be also learning about some forces of interaction. Unlike our covalent bond or an ionic bond having electrostatic forces, or you can say like charges, unlike charges, the forces which we will be studying here is about the intramolecular forces. That is, I would rather say induced dipoles, or I can say weak forces that exist between any two molecules. So to have a clear idea about the nucleus and the electrons which surrounds the nucleus showing different type of forces, I will be posting a video for you to understand how does different intramolecular forces exist between any two molecules, because it includes even hydrogen bond formation. We learned in the last chapter how hydrogen bond is formed between any two molecules in between, that is like hydrogen fluoride or water being one more electronegative than the other. How does it develops a delta positive and negative charges. So here comes a video for you to understand more about the intramolecular forces, because seeing is believing. When you see through videos, you will have the animated impression in your mind, so that will clear all your simple doubts that you have. Then we will get back into the chapter with gaseous state. Types of intramolecular forces. Intramolecular forces are forces of attraction or repulsion between the atoms or the molecules. Intramolecular forces are weak forces. Johannes van der Waals proposed the existence of weak intramolecular forces between the molecules. That's why these forces are also called as van der Waals forces. Let us now learn about the 4 types of intramolecular forces: dispersion force, dipole-dipole forces, dipole-induced dipole forces, and hydrogen bond. Dispersion forces. There are few molecules which are non-polar in nature. In these molecules, the electrons are surrounding the positive nucleus symmetrically. So during this revolving of the electrons around the nucleus, there is no charge developed on the atom. That's why they are non-polar in nature. Now there are chances where the negative electrons, like in case of neon atom, at some times the negative cloud can move to one corner of the sphere, which is our atom. And at this point, the positive nucleus will be on the other end. This unsymmetry will last only for a very few moments. This unsymmetrical neon atom develops a small temporary dipole known as instantaneous dipole. developing a delta positive and negative charge which will attract the electrons in the symmetrical neon atom. Now consider a symmetrical neon atom. So the delta negative charge of the unsymmetrical neon atom attracts the positive charge of the symmetrical neon atom, whereby the electron clouds are moving towards the right. So here a developed charge of positive and negative is again gained in the other atom also. So this atom induces an instantaneous induced dipole in the symmetrical neon atom. These forces are called as dispersion forces or London forces. The interactive energy among these molecules is inversely proportional to the sixth power of the radius, that is the distance between the two atoms. The London forces depends on the size of the molecule, the number of electrons present in the atom or molecule, and the molecular structure. Let us now learn about dipole-dipole forces. These forces exist between the polar molecules like HCl, HF, NH3 and H2O. Let us now consider a HF polar molecule. Hydrogen and fluorine, fluorine being more electronegative, attract the electron towards itself, developing a delta negative charge, hydrogen developing a delta positive charge. Now another HF molecule, when comes in contact, the delta negative charge attracts the delta positive charge of the hydrogen in the next molecule. Such forces are called as dipole-dipole forces or key-sum forces. Here, the dipole-dipole forces are greater than dispersion force, but they are weaker than the ion-ion interaction. It is inversely proportional to the cubic root of the distance between the molecules. Let us now learn about induced dipole forces. Consider the molecule HF, where a delta positive and negative charge is developed, and let us consider an unsymmetrical atom with neon, which is having a negative cloud around the positive sphere. When this comes in contact with hydrogen fluoride, the negative charge in the fluorine attracts the positive nucleus of the neon atom, thereby developing an induced dipole charge of delta positive and delta negative. Such forces are called as dipole-induced dipole force, and it is inversely proportional to the distance between the two molecules. Now let us learn about hydrogen bond, where you can see examples of ammonia, water and HF. You can see the bond formation between nitrogen and hydrogen, oxygen and hydrogen, fluorine and hydrogen. Let's take an example of water, where a delta positive charge is developed on hydrogen atom and a delta negative charge is developed on the oxygen atom. A water molecule is polar in nature, so when another water molecule comes in contact with this, there is a bond developed between the oxygen of one atom with the hydrogen of another atom. Thereby, there is an hydrogen bond formation between the two molecules. Such hydrogen bonds will be developed between other molecules of water when they comes in contact with each other. Such bond formation, we call it as a hydrogen bond. But the hydrogen bond formed is a weak bond, and this keeps on continuing as many as water molecule comes in contact. Let's see the summary here. For dispersion force, dipole-dipole forces, dipole-induced dipole force and hydrogen bond.
Let us now study about the gaseous state, because we have been studying about solid, liquid, gases, and now we have seen
different type of intramolecular forces that are available between any two molecules. Now let us focus on the gaseous state, which we will be studying in this chapter more deeply. Now these are some of the characteristic features of the gaseous state of any molecule. They are highly compressible. If I take a solid, say if I am going to take this duster, I cannot compress it. I cannot compress, that is I cannot press it. It does not go because it is rigid. But if I am going to take any gaseous molecule, it is highly compressible. It exerts pressure in all the directions. The pressure is being released in all the directions. This we have studied in 10th standard, if you remember, children. The pressure of the gas is elastic and it exerts in almost all the walls of the container in equal directions. Gaseous state molecules have lower density than the solid and liquid. So compared to the solid state and liquid state, the density of gaseous molecule is lower. The volume and shape is not fixed because we know they spread in all directions, they move random in all directions. So the volume and shape is not fixed. They mix evenly and completely in all proportions. What is the purpose of studying the characteristic features of gaseous state is because we will be seeing some of the gas laws which we have already learnt in our 10th standard much more precisely to know what role do they play in the gaseous state of the molecule. Now these laws are Boyles Law, Charles Law, Avogadro Law. All these laws put together we will be learning about ideal gas equation. So we have already learnt about Boyles Law in our 10th standard. What does Boyles Law states? At constant temperature and number of molecules, the pressure of a gas is inversely proportional to its volume. That is, being temperature and the number of molecules constant, the pressure of a gas is inversely proportional to its volume. So we write P is inversely proportional to 1 by V, and this shows that whenever there is an increase in pressure, the volume decreases, and whenever the pressure decreases, volume increases. Now to remove this proportionality constant, I introduce a constant here K1. So K1 is called as proportionality constant. So I can write P is equal to K1 into 1 by V. Now if I am going to rearrange this second equation, I get PV is equal to K1, which means at any constant temperature, the product of pressure and volume will be equal to constant. What does it mean, children? Whenever I take a constant temperature and when I take the value of pressure and volume, their product will be always a constant value at different constant temperature. So now let us assume at any constant temperature, the gas has an initial pressure of P1 and volume V1, which on expansion will be reaching a final volume V2 and a pressure P2. So when the initial pressure and volume P1, V1 has increased to P2, V2, what happens according to Boyles Law? We know the product of P1 and V1 is equal to constant. So I'll write P1 into V1 is equal to P2 into V2, which is equal to constant. So what happens here? When I'm going to rearrange this, P1 by P2 will be equal to V2 by V1. Now this equation you can get in your problems where P1, P2 and V2 will be given. They will ask you to find out V1, or any three parameters will be given. You need to find out the fourth parameter. So once we studied this, we came to know that pressure is always inversely proportional to its volume. That is, P1 is here in the numerator side, you can see V1 in the denominator. Increase, decrease. When this is decreasing, V2 is increasing. So now let me plot a graph against pressure and volume. So when pressure and volume graph is plotted at different temperatures, now these are our different temperatures, you can see as the pressure increases, the volume decreases. So this graph shows that there is inverse relation between pressure and volume. Now if I am going to plot another graph between pressure and 1 by V, that is 1 by V is different from V. This shows inversely proportional, and when it is drawn between pressure and 1 by V, It shows a straight line at different temperatures. Now these constant temperatures are called as isotherm. Iso means same, therm means temperature. So at same temperature, the graph is plotted between pressure and volume, where you get an inverse graph and a straight graph when it is plotted between pressure and 1 by V. So this is according to Boyles law. Now let us see Charles law and we'll go to Avogadro. If you see the Charles law in your textbook, page number 138, it's written, the investigations show that for a fixed mass of a gas at constant pressure, the volume and the temperature goes on increasing on a direct relationship. Which means if I am going to take a temperature T, each degree rise in temperature, the volume is increased by 1 by 273.15 Kelvin of the original volume at 0 degrees. What does this mean? If Vt is the final volume at final temperature, V0 is the initial volume, the temperature will be T by 273.15 into V0. So Vt will be V0 into 1 plus T by 273.15, because when we are writing the temperature scale, we never take the degree Celsius into consideration. We need to convert it into the thermodynamic scale. In exam, you will never be asked to write all this, so don't worry about it. Only the problems and the final equation is required. So here T0 will be 273.15. Tt will be 273.15 plus T. Now this is what I am going to substitute in this equation. So Vt will be V0, this is Tt, that is 273.15 plus T divided by T0. So what do I get? Vt by V0 is equal to Tt by T0. What is Vt? Final volume. So V2. V0 is my initial volume V1, which is equal to T2 by T1, which I can also write as V1 by T1 will be equal to V2 by T2. That shows there is a direct relationship between the volume and temperature at constant pressure. So here V is equal to K2 into T, which shows that when you divide the volume by temperature at constant pressure, that is isobar, that is the pressure is remaining constant, and if I am going to draw a graph between volume and temperature at constant pressure, I get a straight line. So what does Charles law state? At constant pressure, the volume of a gas is directly proportional to its temperature at Kelvin scale. So this Kelvin scale is nothing but 273.15 will be added to the 0 degree Celsius, whichever is given to us. So these two laws are important. Next we will get back into Avogadro law. Gay-Lussac's law. So we have seen what is Boyle's law, what is Charles law. In Gay-Lussac's law, it says that at constant volume, that is any gas at constant volume, the pressure will be directly proportional to the temperature. So as the pressure of the gas increases, the temperature also increases, which means P by T is equal to K3, which is again the proportionality constant. Now as we have drawn the graph for Boyle's law and Charles law, if we are about to plot a graph for pressure versus temperature at constant volume at 3 different constant volume, which will be called as isochord, we definitely get a straight line, because pressure increases, the temperature also increases. Now these experiments were being done by the scientists at various different volumes, making the volume to be at constant, checking what happens when the pressure of the gas increases, whether the temperature also simultaneously increases. As there were different experiments done at different constant volumes to check the variability, whether they are really directly proportional or they are inversely proportional, they came to know that they are directly proportional, which means both of them increase together and they decrease together. As there is an increase in the pressure, temperature gradually increases, and when there is a decrease in pressure, temperature gradually decreases. So this is the law which is being stated by Gay-Lussac. The next comes the Avogadro law, which we have already learnt in our 10th standard, that is keeping temperature and the pressure constant, volume is directly proportional to number of molecules or number of moles. Now this is also being restated that equal volumes of all gases at same temperature and pressure will have equal number of molecules. Here V is proportional to N, where V is equal to K4N. Again K4 is the proportionality constant which is used to remove this proportionality symbol. And we know when we take 1 mole of a gas, because here we are studying with respect to 1 mole. So when we consider 1 mole of a gas, number of molecules in 1 mole of a gas will be 6.022 into 10 raised to 23. This we have been learning from 10th standard, if you remember, Na as an Avogadro number. So the number of molecules present in 1 mole of any gas will be 6.022 into 10 raised to 23, which is the Avogadro constant or the Avogadro number. So here STP at any standard temperature pressure condition, the gases will constitute the same volume. So when I say standard temperature, which is 273.15 Kelvin at 10 degrees Celsius and the pressure being 1 bar, the volume will be 22.7 liter per mole. This is for an ideal gas at standard temperature and pressure. So with this, these two laws have been over. Now we will talk about the molar volume with respect to density also.
Let us see about the number of molecules in a gases. How to find out the number of molecules of a gas? We know number of moles is equal to m by m, where m is the mass of the gas and capital M is the molar mass. This we have learnt in number of moles. So when I know that volume, that is in Avogadro law, volume is equal to K4 into m by m, because I am substituting the value of n here, m by m. When I rearrange this equation, so capital M becomes K4 into m by V, where mass by volume is equal to density. So K4 into density. Now why I am saying all this is, any gas that behaves according to Boyles law, Charles law and Avogadro law will be called as an ideal gas. That ideal gas is a perfect gas which does not have any intramolecular forces of interaction. There are gases which are real gas which deviate from this behavior according to the laws and under certain specific conditions. Those are called as real gas. Now if you consider the equation according to Boyles law, that is at constant temperature and number of moles, it will be volume is inversely proportional to pressure. If you take at constant pressure and number of moles, volume is directly proportional to temperature. If you take Avogadro law at constant pressure and temperature, volume is directly proportional to number of moles. So when you take volume is proportional to Nt by P together with all the three equations, we take PV proportional to Nt. To remove this proportionality, I introduce a constant which is R. So PV is equal to nRT, where R is called as a universal gas constant. Now this equation we call it as an ideal gas equation. So in ideal gas equation comes in 2 marks, derivation of ideal gas equation, so which is already given there, and you can see the value of R being 8.314 joule per Kelvin per mole. So this is also gives an this gives a relation between the various variables like pressure, volume, temperature and number of moles. So this is also called as equation of state. So now children, with this this topic, or I will stop here with this topic. The next topic we will be learning in the next class. Regarding intramolecular forces also, I will try to post a video so that you can understand better what is a van der Waals force, what is a dispersion force or dipole forces. Okay. Thank you children. Have a great day. Bye.
Gas laws. Some of the physical properties of gases are highly compressible. Gases exert pressure equally in all directions. They have much lower density than solids and liquids. The volume and shape of the gases are not fixed. Here we will be learning about some of the gases, their laws, because these gases, they mix evenly and completely in all the proportions. Now, these properties of the gases are governed by few gas laws. They are Boyles Law, Charles Law, Gay-Lussac's Law, and Avogadro's Law. Let us learn each law one by one. Let us now learn about Boyles Law. To explain Boyles Law, let us learn through a small experiment. There is a glass jar which has got a covering on the top. There is a deflated balloon inside where the pressure is very high. So, the air present inside exerts high pressure. Now, if the air is being sucked out of the glass jar, there is vacuum inside which has created low pressure. Now, that makes the balloon inflated. So, the size of the balloon increases as the pressure becomes low. Now, again, if the bottle is open, the air outside reaches inside the bell jar, creating a high pressure. As soon as a high pressure is created in the bell jar, the size of the balloon decreases, it becomes deflated. So, from this experiment, we can understand that at constant temperature, the pressure of a gas is inversely proportional to its volume. So, P is inversely proportional to 1 by V, PV is equal to K, where K is the proportionality constant. From this, P1 V1 equal to P2 V2, or P1 by P2 equal to V2 by V1. Now, let us move to Charles' law. Now, considering Charles' law, let us take two inflated balloons and let us put the first balloon inside a jar which is being heated at high temperature. Let us make the second balloon inside the jar which is kept in an ice tray. After some time, you can see the size of the balloon which is under the high temperature of heating. It increases, it becomes more inflated, while that of an ice jar decreases. So that shows as temperature increases, volume also increases, where V is directly proportional to T at constant pressure. So from this, it is very clear that V by T is equal to constant. Hence, V1 by T1 is equal to V2 by T2. Let us now move into the third law, which is Gay-Lussac's law. Consider a bottle which contains a paper that is slightly lit, and when it is inserted into the bottle, and if the bottle is being closed with an egg, after some time, with the support of oxygen, the paper was burning. Quite after some time, at low pressure, the balloon, at low pressure, the fire is being off and this egg is moving inside. So the high pressure which is created inside because of the temperature pushes the egg inside the glass jar. Here, pressure is directly proportional to temperature, which means as pressure increases, temperature also increases. Therefore, P by T equal to constant, P1 by T1 equal to P2 by T2. Let us now move into the last law, which is Avogadro's law, which shows volume is directly proportional to number of molecules. Consider a balloon which is being inflated. When air passes inside, you can see the size of the balloon increases. That shows that there are number of molecules which are entering the balloon also increases. So as the number of molecule increases, the size will become more and it occupies the entire balloon. And as the air is being released or deflated, the number of molecules has been pushed out, so the balloon becomes small. So that shows volume is directly proportional to n, and V by n is equal to constant. And here, with volume and number of molecules, the Avogadro's law is getting over. So this is a summary with Boyles law, Charles law, Gay-Lussac's